Imagine, for a moment, that you are floating in the vast, dark emptiness of space. Below you is a beautiful blue and white marble, swirling with clouds and shimmering with oceans. This is our home, Earth. It is not sitting on anything. It is simply hanging there, in the cosmos, a giant rock, hurtling through the void. It seems so still, from our perspective down here, but it is constantly in motion. We are all passengers on this cosmic spaceship, spinning at over 1,000 miles per hour, while also orbiting a star at an astonishing 67,000 miles per hour. It's a journey we all take together, every single day of our lives, across the grand theater of the universe. Our cosmic neighborhood is quite busy. Earth is not alone. It shares its space with other rocky worlds, like Mars and Venus, and giant balls of gas, like Jupiter and Saturn. There are also countless smaller rocks called asteroids and comets, zipping around. All of these objects are held in a delicate dance by an invisible force, tethered to the center of our solar system, a star we call the Sun. This star is the powerhouse of our neighborhood, a gigantic nuclear furnace that bathes all the planets in light and warmth. The universe is a grand stage, and everything on it, from the smallest pebble to the largest star, is participating in an intricate performance. It might feel strange to think of our solid ground as just a rock floating in space. We feel so anchored, so firmly planted. If you drop your phone, it falls straight down, not sideways, or up into the sky. This simple observation is a clue to one of the most fundamental rules of the cosmos. There is an invisible string that pulls everything towards the center of our planet. This force not only keeps our feet on the ground but also holds our atmosphere in place, giving us air to breathe. It is the silent conductor of our daily lives, a fundamental property of the universe that governs motion everywhere. For thousands of years, humans looked up at the stars and planets, wondering why they moved the way they did. Why did the moon circle the Earth? Why did the planets wander across the night sky in predictable paths? They seemed to follow a set of rules, but nobody knew what those rules were. It took a brilliant mind, a revolution in thinking, to finally connect the falling of an apple on Earth to the grand celestial waltz of the planets. This journey into understanding began with a simple question: why do things fall? The answer would forever change how we see our place in the cosmos. Let's travel back in time to 17th century England. Here we meet a man named Isaac Newton, one of the greatest scientific minds in history. The story goes that he was sitting under an apple tree when an apple fell, bonking him on the head. This simple event sparked a universe-changing idea. He wondered, if a force pulls this apple to the ground, could the same force reach all the way up to the moon? Could that be the very thing that keeps the moon from flying off into space? He realized the force that makes an apple fall and the force that keeps the moon in orbit around the Earth are one and the same. He called this force gravity. Newton didn't just name gravity, he described it with mathematics. He came up with 3 famous laws of motion. His first law says an object will stay still or keep moving in a straight line at a constant speed unless a force acts on it. A football on the grass won't move until you kick it. His second law connects force, mass, and acceleration. It says that the more massive an object is, the more force you need to make it speed up. It is much easier to push a toy car than a real car. His third law is simple but profound. For every action there's an equal and opposite reaction. When you push against a wall, the wall pushes back on you with the same force. So, what is the difference between mass and weight? Mass is the amount of stuff an object is made of. Your mass is the same whether you are on Earth, the moon, or floating in deep space. It is a measure of your inertia, your resistance to being pushed around. Weight, however, is the force of gravity pulling on that mass. On the moon, where gravity is much weaker, you would weigh only about 1/6 of what you weigh on Earth. Even though your mass, the amount of you, hasn't changed at all. You could jump much higher, but you would still be just as difficult to push over. This invisible force of gravity governs the entire cosmos. It is why we stick to the Earth, why the Earth orbits the Sun, and why the Sun is part of a giant spinning collection of stars, called the Milky Way galaxy. Gravity is a long-range force that pulls all objects with mass towards each other. The more massive the objects and the closer they are, the stronger the pull. The Sun is incredibly massive, so its gravitational pull is strong enough to keep all the planets, including our own little rock, in a constant, predictable orbit, dancing around it for billions of years. Have you ever wondered why your phone screen shatters when you drop it? The answer lies in a concept called energy. When you lift your phone, you are doing work against gravity, giving it what scientists call potential energy, stored energy, ready to be used. The higher you lift it, the more potential energy it has. When you let go, gravity pulls it down, and that stored potential energy is converted into kinetic energy, the energy of motion. The moment before it hits the floor, all that stored energy has become movement. That kinetic energy has to go somewhere upon impact, and it does so by breaking the chemical bonds in the glass, creating a spiderweb of cracks. Energy is a bit like a magical currency for the universe. It can't be created from thin air, nor can it be destroyed. This is the law of conservation of energy. It only changes from one form to another. Think about a basketball. When you eat your breakfast, the chemical energy in your food is converted into energy your muscles can use. You use that energy to throw the basketball towards the hoop. The ball has kinetic energy as it flies, but as it rises, it slows down, trading kinetic energy for potential energy. As it falls back down, that potential energy turns back into kinetic energy, ready for a satisfying swoosh through the net. Now let's talk about another fundamental force, one that is far stronger than gravity: the electromagnetic force. This is the force behind electricity and magnetism. Everything is made of tiny atoms, which have even tinier particles inside them with a property called electric charge. Some particles, called protons, have a positive charge, while others, called electrons, have a negative charge. Just like with gravity, there are rules. Opposite charges attract each other, while like charges push each other away. This force is what holds atoms together, making it responsible for almost everything you see and touch. When electrons flow through a wire, we call it an electric current. Think of it like water flowing through a pipe. The push that makes the electrons move is called voltage, and the narrowness of the pipe that resists their flow is called resistance. This flow of charge powers our world, from the lights in our homes to the computer you might be reading this on. In the 19th century, a physicist named James Clerk Maxwell showed that electricity and magnetism were two sides of the same coin: electromagnetism. This force is billions upon billions of times stronger than gravity, but we don't usually feel it on a large scale because most objects have a neutral balance of positive and negative charges. If you could zoom in on anything, your hand, a glass of water, or even the air you breathe, you would find that it's, well, not solid at all. Everything is made of these impossibly small building blocks called atoms. Think of them as the fundamental Lego bricks of the universe. There are actually over 100 different kinds of atoms known as elements, like hydrogen, oxygen, and carbon. When these atoms join together, they form molecules. For example, a water molecule is made of 2 hydrogen atoms bonded to 1 oxygen atom. All the incredible variety of stuff in our world comes from the countless ways these basic atomic bricks can be combined. For a long time, people thought atoms were the smallest things possible. But, as it turns out, we've since discovered that they're made of even smaller, or subatomic particles. In the center of every atom is a tiny, dense nucleus, which contains positively charged protons and neutral particles called neutrons. Whizzing around this nucleus, in a sort of cloudy haze of probability, are the tiny, negatively charged electrons. It's the attraction between the positive protons in the nucleus and the negative electrons that holds the atom together. The vast majority of an atom is, believe it or not, actually empty space, a mind-boggling truth about the solid world we perceive. This subatomic world is also where we find the true nature of light. For centuries, scientists argued about whether light was a wave, like a ripple in a pond, or a particle, like a tiny bullet. The incredible answer is that it's both. Sometimes light behaves like a wave, able to bend around corners and interfere with itself. That's why we see rainbows. A prism splits white light into a spectrum of colors, just like waves of different lengths. This wave-like nature allows light to travel through the vacuum of space, from distant stars to our eyes, carrying information across the cosmos. In other situations, though, light behaves as if it's made of tiny packets of energy called photons. Think of it as a stream of tiny particles. When light hits a solar panel, it's these individual photons that knock electrons loose, generating an electric current. This strange dual identity is called wave-particle duality. and it's a cornerstone of the bizarre rules that govern the quantum realm. Light isn't simply a wave or a particle, it's a quantum thing that reveals one aspect of its identity, depending on how we choose to observe it. A first glimpse into the profound weirdness of reality, at its most fundamental level. At the beginning of the 20th century, another genius came along who would once again revolutionize our understanding of the universe. His name was Albert Einstein. He realized that something was missing from Newton's picture of gravity and motion. So, he proposed his theory of relativity, which revealed a deep connection between space and time. He imagined them as a single, four-dimensional fabric. Space-time. Massive objects don't just pull on each other with a force. They actually warp and curve this fabric. It's this curvature of space-time that we experience as gravity. Planets orbit the sun not because they're being pulled, but because they are following the straightest possible path through curved space. Einstein's theories led to some very strange but true predictions. He showed that the speed of light in a vacuum is a cosmic speed limit. Nothing can travel faster. As you approach this speed, weird things happen. Time itself begins to slow down for you relative to someone standing still. This isn't science fiction, it's a measurable fact, confirmed by incredibly precise atomic clocks on fast-moving satellites. He also gave us the most famous equation in all of physics, E equals mc squared. This elegant formula reveals that mass and energy are two sides of the same coin. It means a tiny amount of mass can be converted into a tremendous amount of energy, which is the secret behind the power of the sun and stars. But, the universe gets even stranger when we look at the very, very small. This is the domain of quantum mechanics, the physics of atoms and the particles within them. In this realm, the predictable, clockwork rules of Newton and even Einstein break down. Particles don't have definite locations until we measure them. They exist in a cloud of possibilities. It's a world governed by probability and uncertainty. A core idea is the Heisenberg uncertainty principle, which states that you cannot simultaneously know both the exact position and the exact momentum of a particle. The more precisely you know one, the less you know about the other. This cosmic dance, from the predictable waltz of the planets to the frenetic, uncertain jitterbug of quantum particles, is the story of physics. It's a story of human curiosity, of looking at the world around us and asking, why? From Newton's falling apple to Einstein's curved space-time and the ghostly nature of the quantum world, we have peeled back layers of reality to reveal a universe far more intricate, mysterious, and beautiful than we ever could have imagined. And the most exciting part, the dance isn't over. There are still deep mysteries waiting to be solved, and the next great idea could come